All right, so I would like to look at this example here where we have a 100 kilogram box of dimensions of 50 centimeters by 50 centimeters by 50 centimeters, and it is resting on a flatbed truck, on the back of a flatbed truck. They say take the coefficient of static friction to be 0.4 and the coefficient of kinetic friction to be 0.2. Then it says here, what is the maximum acceleration of the truck, or what is the maximum acceleration the truck can have without the box slipping? So to demonstrate that, here is a wheel here, and it's flat, like a flatbed truck. And here's another box, but some weight. So the truck here is horizontal, and it's at rest. If I started to accelerate, the mass will move. And the mass will move with it. Think about why. So I'm pushing on the truck. So why does the mass accelerate? A force must be applied to it. You might say it's my force, I'm pushing, but my force is pushing the truck, not the mass. Not the mass. So who is pushing the mass? Who's responsible? The answer is, imagine if this were perfectly slippery, then the truck will move and the mass will just remain at the same point. If it was perfectly slippery, it's like it's not even resting on it. So in fact, it's actually the static friction that's moving it. You might say, well, if it's moving, why is the friction static? It is static because this will be kinetic if these two materials rub against one another. That's kinetic friction. There is relative motion between the two surfaces. If there isn't, meaning this mass and this, they move together, then it is static friction. So in fact, it is the static friction between the mass and this surface here is what's accelerating this mass. So it is the static friction between the flatbed truck and the box that caused the box to accelerate. So if I accelerate it, it will move. However, if I accelerate a little too much, that's fine. If I accelerate it way too much, so let's see, you see the mass slipped back because friction, static friction, remember, it has some maximum value. So it will accelerate you, but it can accelerate you only so much. If the truck accelerates way too much, the force of friction is not enough to generate that kind of an acceleration, and so the thing will start to slip. Okay, I hope that brings the point, demonstrates that. Okay, so let me move this away. Okay. So let us draw a picture first. Here is the bed of the truck, and here is the box. And look here, they give you the dimensions of the box. They don't matter, the dimensions. Remember, the friction does not depend on the surface area in our simple model. It doesn't depend on the surface area. And so here's the truck, and then it will accelerate this way, a certain acceleration. That's the direction of the acceleration. So the forces are on the box. Of course, there is gravity. And then there is the normal force. And the acceleration is this way. So the only force that's causing this box to accelerate is the force of static friction. The force of static friction is causing it to accelerate that way. So the force of static friction will always point in the direction of opposite to where the would-be motion. Let me make sure the camera is close enough and zoomed in. Yeah, let me move it closer. Okay, I think this is better. Yeah, okay, it's closer. So the box wants to slide backward, but friction will push it forward. And I know it's forward because the box is accelerating and moving along with the truck, and it's accelerating like that. So that's that. So I know that the net force in the y direction, the net force is 0 because the truck is not going up or down. The box is not going up or down. So the net force in the y direction is 0. It means the normal force is equal to mg. Normal force is equal to mg. So the force of static friction, and in this case, to cause the maximum acceleration, you need maximum force. So I want the maximum force of static friction. And the maximum force of static friction is equal to mu s times the normal force, but the normal force is mg. mg. Okay? And so we say the net force in the x direction is equal to the mass times acceleration in the x direction. The x direction, the net force. The x direction is equal to the mass times the acceleration in the x direction. And by the way, as usual, if it's everything is horizontal, this is the x direction, and this is the y direction. The only force in the x direction is the force of static friction, the maximum one. I want it to be the maximum, because remember, static friction takes values between 0 to some maximum value, and I would like it to be the maximum it is. Beyond that, it just can't keep up. So mu s mg. So I have mu s mg equals to the mass times acceleration, so ma. The mass cancels. Again, the mass of the box does not matter. And so the acceleration is just mu s times gravity. And mu s is 0.4 times 9.8. So 0.4 times 9.8. And let me get my calculator here. 0.4 times 9.8. 3.92 approximately. About 3.9. So if the truck accelerates at 3.9 meters per second squared, friction is able to give you that kind of an acceleration. If the truck accelerates at, let's say, 4 meters per second squared, then the force of static friction is not able to keep up with it. It's only able to give you 3.9. And so beyond that, the box will start to slip and maybe fall off the truck if it's not, if it's not secured or whatever. Okay. All right. So far we have dealt with motion with constant force. I would like to now do an example where the motion is at a variable force, and see how we can deal with it. Newton's second law applies. Still, it says the net force equal to the mass times acceleration, and we go from there. So let me show you this. We have here a force Fx equal to some constant c times the sine of pi times the time t, and then capital T here, where c and t are constants. We'll give you those constants in a moment. And this force is applied to an object of mass m. So the object has mass m, and we're applying a force to it in the x direction. And the object will move on a frictionless surface. So if the surface is frictionless, horizontal, it means that the only force on it, there is no friction or anything else. Of course, there is gravity and normal force, but those are in the upward direction. So the only force in the x direction is this force, and that force will cause an acceleration. So I know that the net force in the x direction will equal to the mass times the acceleration in the x direction. I'm talking about the x direction, so clearly this is a in the x direction. And so I get the net force is c, this constant c, times the sine of pi times the time divided by capital T, and that's equal to the mass times the acceleration. Okay, and so the acceleration is equal to c divided by m times the sine of pi times t over capital T. That's the acceleration. So I found the acceleration, fine. They say the object is initially at rest, and it's at the origin, meaning the position x initial is 0 and v initial is equal to 0. Right? So here, v at time t equal to 0 is 0, and x at time t equal to 0 is 0. So we're given those initial conditions. So they say find an expression of the object's velocity and then graph your result for this time interval. Let's find an expression for the object's velocity. You see here the acceleration is a sinus, depends on the sine of pi times the time divided by capital T. Pi is a constant, capital T is a constant. So it's the sine of something times the time. So the acceleration is not constant. But the acceleration is dv dt. I know that dv dt is the acceleration, and that's equal to c over m times the sine of pi t over capital T. So I integrate both sides to get v. Derivative of v gives me this, so v itself is the antiderivative of this. So the antiderivative of sine is negative cosine, so you would have negative. I still have the c over m, and then I have the cosine of pi t over capital T. Okay? And then, so I have to add something else here. Because when you take the derivative of cosine, it gives you a negative sign. So that's fine. Negative will cancel the negative and give me positive sign. But the chain rule will give me, you have to take the derivative of this with respect to time. That will give you a pi over t out. So when you integrate, you have to multiply by the reciprocal of that. So that's capital T over pi. So now when you take the derivative of cosine, you get negative sign. That takes care of that. And then when the chain rule gives you a pi over t out, that gets cancelled by the t over pi, and so you get this result. So v is equal to this. But that's not it, because when you take the antiderivative, it always gives you some arbitrary constant c. Well, we have the letter c here. Let's see, what can we give? Let's use the letter b for the arbitrary constant. Okay. Great. So now, but what is that b? What is that arbitrary constant? Well, it's arbitrary, and you can only determine it if you're given the initial conditions, which we are. We're told v at time t equal to 0 is 0. So here is v. I'm going to plug in at v at time t equal to 0. We will plug in 0 here for t. So I get negative capital C over m, and then capital T over pi, over pi, and then the cosine of 0, basically, right? Pi times 0 over t is 0. So cosine of 0 is 1, so I just get that, plus b, right? Because the cosine of 0 is 1, so I get that. And I'm told that v at time t equal to 0 is 0. Therefore, this constant b will equal to, just move this from the other side to the other side, so it would be ct over pi m, or m pi. I'll call it pi m. So c capital T over pi times m. So the full expression for the velocity now, since we have determined what b is, so we get that v as a function of time will be negative ct over pi m times the cosine of pi t over capital T plus this constant b, plus the constant b, but the constant b is capital CT over pi times m, and we can factor the CT pi m, pull it outside, so you get CT over pi m times, when you take this out, you just have a 1 left, minus, when you take this out, you have just a negative cosine. Negative cosine of pi t over capital T, like so. Okay, so that's that. Sounds good. And now we have to plot this. So let's plot it. Let's plot it, see what happens. V as a function of time. Here is the time. Here is V. At time t equal to 0, the velocity is 0. Let's see if that verifies. So at t equal to 0, you plug in 0 for t, so you have cosine of 0 is 1, so you have 1 minus 1, that's 0. So it starts there. And then what does it do? What does it do? It will, when the cosine is 0, so this is a cosine function, so it will grow. 1 minus, it will grow to here. When is it maximum? Well, it's maximum when the cosine is, actually, I'm sorry, somewhere here, its maximum when the cosine is actually negative 1. So it will grow all the way to some maximum value. So when is the cosine equal to -1? Cosine is -1 when the argument here is 3 pi over 2. 3 pi over 2. And then the velocity will start to drop when the cosine again is 1 at 2 pi. 2 pi, let's say. So they wanted between 0 and capital T. So when T is equal to capital T, I have here capital T over capital T is equal to 1. So this is the cosine of pi, that's -1, and minus 1 is 2. So in fact, we have this. I should have plotted it ahead of time. So this is when T is equal to capital T, we get this. And this maximum value of velocity is what? 1 minus 1 is 2, so it's equal to, this value here will be twice this number. C capital T over pi m. Okay. Okay. And yeah, so I have that. What's the next one? What is the maximum? What is the maximum velocity of a 500 gram? What's the maximum velocity? Yeah. What is the maximum velocity of a 500 gram object if c is 2.5 and capital T is 1? Well, this is the maximum velocity. It can reach up to here. That's V max. So for part B, V max is equal to twice C capital T over pi m. By the way, I think I messed up here. So the shape should look like that. Yeah, I think it should look like that. Right. Yeah, it should look like that. Anyways, but that doesn't change the fact that this is the maximum. The maximum is that. All right. You can always plot it in your calculator. So they're given a C and capital T, so I get V max equal to twice. C is 2.5, 2.5. Capital T, they're telling me it's 1. Pi is, well, 3.14, approximately 3.14. And the mass is 500 grams, that's half a kilogram, so 0.5. 0.5. And I need my calculator here. So I get, let's say, 2 times 2.5 over pi, and times 2, 3.183. 3.183. So that's about 3.2 meters per second. Okay. So that's that. That is that. And if they ask you what is the position as a function of time, they didn't, but just as an exercise, So here is v of t. Here's v of t. Let's write it down, and then we want the position as a function of time. That also can be done. So let me just write it. I'll write it down here, so I don't forget it. So I have v of t is here, this one, ct over pi m cosine of this, ct over pi m times the cosine of pi t over capital T plus ct over pi times m. That's the velocity. So let's see what the position is. We know that the position at t, I think, yeah, I forgot a minus sign here. Forgot a minus sign there. So if I want the position, position is the derivative of velocity, so, I'm sorry, velocity is the derivative of position, so the position will be the integral of this. So x as a function of time. Let's integrate this. You integrate cosine. The derivative of sine is cosine. So you would have minus c capital T over pi times m times the sine of pi t over capital T. But then when you take the derivative of pi over t comes out, so you have to multiply by t over pi. T over pi. The integral of ct over pi m will be plus c capital T over pi m times little t, because the derivative of this will just give me ct over pi m. And then plus some arbitrary constant. Earlier I called the constant b, I would call it, we use the letter c, I'm going to call it d. D. And then what is d here? Well, at time t equal to 0, the position is 0. So if you plug in t equal to 0 here, you get, well, sine of 0 is 0. That will just get rid of this whole thing. That's a 0. And then ct over pi m at t equal to 0, that's a 0. And I would like, when I plug in 0, I get 0. So d itself has to also be 0. So 0. That means my position as a function of time, x of t, will simply equal to minus c over m, t times t and pi times pi, that's t over pi squared, sine of pi t over capital T, minus sign is still there, plus c capital T over pi m. That's the position as a function of time, and of course you can plot that. It will be like a sine function and a linear function on top of it. So it would be like an increasing sine function, basically. It will just be going up and going up and down. So try to plot that if you want on in Wolfram Alpha, the one I showed you last time, or your graphing calculator. You have C, you have the mass, 500 grams. C is 2.5. Capital T is 1. So try to plot it. I would say go for it. And so I will stop here. Next time we're going to do end of chapter problems.